So number 4 asks describe all integers m such that 5m is not a multiple of 4. So immediately what we can do is rewrite 5m. That's p to the 1a, a1, p2, a2, dot dot dot, p to the n, a to the n. So then remember m is multiplicative if you choose making sure the GCD of p1, well, m is multiplicative. This function is multiplicative if you choose the right factors like any prime combinations, because we know that p1 and p2, the GCD is always going to be 1. So if I were to calculate 5p to some power a, remember that's pa times the product of all the primes that divide into pa minus. Well, in this case, it's just going to be p. So it's p to the a times 1 minus 1 over p. That's p to the a minus p to the a minus 1. And then I factor out a pa minus 1 times p minus 1. So the reason he'll do this step is I'll explain a little bit later, and I'll kind of circular. It's kind of circular logic, but it makes sense the why he set it up like this. So before we move over, let's talk about what we have. We're trying to prove that 5 to the m is not a multiple of 4, and trying to describe those integers that satisfy that. So with that, we can describe in terms of modular arithmetic. Because if it's a remainder, if I take mod 4 and has a remainder of 0, well, that means it's a multiple of 4. So I just choose, so I'm looking for the mods of 1, 2, and 3. So let's identify, when is it 0 mod 4? Well, if it will be 0 mod 4 if this entity, p minus 1, is a multiple of 4. So if I plug in 5 for p, then 5 minus 1 is 4, right? So it doesn't matter what this is. This could be 107, but because I'm multiplying by a multiple of 4 here, whether this be 4, 8, 12, whatever, it's still going to give me 0 mod 4 when I take the modulus of it. So notice that, well, if I take P5, P9, P17, as long as it's a multiple of 4, I'm good. So I can represent that as if P equals 1 mod 4. Right? Because 5, 9, 13, 17, etc. And if easier way, if I plug in 1 here, 1 minus 1 is 0. So the whole thing will be 0, which is what I'm looking for. But what about the other case, 0 mod 4? Well, it's still 0 mod 4, but what if this was a multiple of 4? How would I do that? Well, for one thing, the only way this is a multiple of 4, well, this prime has to be 2. Right, because if I use any other prime, it's going to be an odd. And I'm multiplying a bunch of odds together, that's no way it's going to be divisible by 2. Furthermore, never by 4. So the only way this can ever be at least 4 is if a is greater than 3. So why is that? If I plug in 3, that's 4 already, right? Because 2 squared. And continue on, 2 cubed, 2 fourth, 2 to the 5th. They're all divisible by 2 squared. Therefore, they're divisible by 4. Since they're divisible by 4, if I take mod 4 of it, I'm going to get 0. Now let's look at the other case. How do I get 1 mod 4? Well, I get 1 mod 4 if this can get me 1 mod 4. How do I do that? Well, again, if I take a number like p equals 2, if p is 2, then immediately I'm going to get a remainder of 1. So 1 mod, taking mod 4, that's going to give me 1. So if p equals 2. Right? But we got to account for the other. In this case, look what happens here. Because now I have 2 here. But this will give me a remainder of 4 if this is a equals n. A equals 1. Because 2 to the 0 is 2. And then 2 times 1 is... this will give me 2 to the 0. And that's 1. So the reason is like p equals 2 here. So that gives me 1. But because in this specific case, p equals 2 will affect it. Because if I have too many 2's here, that's going to be divisible by 4 because of the previous logic. So think what happens if a equals 2. 2 minus 1 is 1. So 2 to the first is 2. Right? So 2 mod 4 isn't 1. That's 2. So I have to restrict this and make this specifically 1 by making it a equals 1 to give me a 0 exponent. And because of that, there's no other conditions that can get me 1 mod 4. So let's see what happens if this is 2 mod 4. How do I get that? Well, there's going to be 2 situations. how can I get this such that it's 2 mod 4? Well, the obvious case is just going to be P equals 2 mod 4. Sorry, 3 mod 4. Yeah, math wrong. So with 3 mod 4, let's do the numbers. 3 minus 1 is 2. 7 minus 1 is 6. So mod 4, that's 2, etc. If I do, let's see, 18. 18 minus, 3 mod 4, 7 mod 4, 7, 15. 15 minus 1 is 14. 14 mod 4 is 2. So it doesn't matter what this is going to be. This is always going to be 3 mod 4. So 3 minus 1 is 2. So it'll always give me a remainder of 2. In the other case is, if 2 mod 4, I gotta look at the other factor. How will this factor ever give me 2 mod 4? Well, this is a bit restrictive, right? So I gotta say p equals 2 at least, because everything else is gonna be an odd number. And those odd numbers are gonna be mod 1 or mod 3, so not mod 2. Again, by that I mean, if I have an odd number for prime, remember any odd number mod 4 only has 2 conditions. It's going to be 1 or 3. So it has to be even. To be even, p has to be 2. And then the only other case is, and a has to equal 2. Because if a is greater than 2, then I have mod 4. So again, plug in a equals 3. This gives me 2 squared, which is divisible by 4. But if I have a equals 2, I have a quantity of 2 to the 1, and that's going to give me mod 2, or give me 2 when I do mod 4. The last case is, when is it going to be 3 mod 4? So that means I want this difference to be 3. So people had remember that this has to be a prime number. So I can't, well, this has to be, the difference has to be 3. So normally I would plug in 4 here, right? But that doesn't work because that doesn't work because we can never have a prime such that when you minus 1, we're going to have a 3 mod 4. And same thing here.